probability a little deeper. Probability is a ratio, so that fits great in this unit. If you want to know the probability of something, let's call it n, happening, then you make a ratio out of the number of outcomes that look like n. I'm calling it the number of n-type outcomes. Any outcome that satisfies this goes in the top, divided by the number of all possible outcomes. And this gives us a ratio that expresses how likely it is that n will happen. Okay? A couple of things to keep in mind. For the answer, you want to start out as a fraction and reduce it. Those are the only two requirements. Now, there may be equivalent percentages or decimal forms, and you could change it to one of those, and if they're exactly equal, all those answers are fine. But you should definitely avoid rounding. There's no reason to change it to a decimal if it requires you to round it off when the fraction was an exact answer to begin with. That's better. Okay, here's an example of what I'm talking about. Probability of rolling an even number on a standard die. Well, there's numbers 1 through 6, so that would be either 2, 4, or 6. There are 3 even numbers, and there are 6 numbers all together. There's my fraction. I reduce it. I'm done. It's 1/2. Now that's equal to 50%. That's equal to 0.5. And casinos love percentages, but math teachers prefer fractions. So I would rather you just leave it like that. Okay, let's talk about some vocabulary that has to do with likelihood. Here's my weather forecast for this weekend. Looks like we have a 60% chance of rain-snow mix. So rain and snow is likely. Likely is anything greater than 50%, which is the same as greater than 1/2, right? Unlikely would be less than 50% chance. Certain is only the case when it is a 100% probability, and impossible is 0%. Sometimes I have students who don't want to calculate the 0. They're afraid there's something wrong if they get 0 for an answer. That just means that you are asked the probability of something that cannot happen. It's impossible, and that is the correct answer in that case. Equally likely is 50%, of course, or 1/2. Okay, let's talk about the basic counting principle. We use the basic counting principle to calculate all the outcomes when we have different categories. We have parts of the outcome. In this case, at a sandwich shop, you choose from kinds of bread, fillings, and the little toppings that you put with the fillings, right? There's different categories, and all these things are combined into the outcomes. When you have that situation, what you do is multiply together the options for each of these. Okay, so if we want to know how many different sandwich outcomes are possible, we're going to multiply all the possibilities for these 3 categories. Okay, so for kinds of bread, clearly there are 3. For sandwich fillings, there are 6 different ones. Toppings is a little different. It says you can choose 3 different toppings. You have 8 to choose from. So there's 8 different kinds of toppings, and you get to choose 3. So when I'm multiplying all my options, this looks a little different. I've got kinds of bread times kinds of sandwich fillings times, and I have 3 different toppings I get to choose from. How many toppings do I have to choose from for each of these? These are 3 separate things on the sandwich. Well, I have 8 to choose from for that first topping. Since they all 3 have to be different, so I've already chosen one of them, I can't choose it again for the second one, so that eliminates one of the toppings. Now I only have 7 to choose from, and then I'll only have 6 to choose from for the last option. So these are all the different things that can be put on the sandwich. You need to multiply all 3 of those together to find out all the possible combinations at this sandwich shop. So let's do that. I get 6,048 different sandwiches. Wow, that's a lot of choices, isn't it? Now I have a probability question for you. What is the probability that if you chose everything at random, it would end up being this sandwich? Let's find out. For our sandwich this time, for bread, I'm being very picky. I only want this one choice. So I'm going to take 1 for that. For my filling, same thing. I'm going to be very picky. I only want tuna, so that's just one choice. But for the toppings, I don't really care. That means that part is going to be the same as this. I can choose out of 8 things, out of 7 things, out of 6 things. And that is my numerator because that's going to tell me how many combinations at the sandwich shop fit with my criterion. Now the denominator is what we already calculated. These are all the possible sandwiches, and so that is going in the denominator. This is the beginning of our fraction. We're going to calculate it and reduce it, and that is the answer. So let's see what's in the top. Okay, when I multiply those, I get 336, and the denominator is still 6,048, and we need to reduce that. I can divide everything by 3 to get started. Now, using my divisibility rules, I notice that this ends in 12 and this ends in 16, so I can definitely divide both of those by 4. Let's see what that would be. Okay, 28 over 504, I can divide that by 4 again, can't I? Okay, now that doesn't reduce unless 126 is divisible by 7. And it is. Turns out that 7 goes into 126 18 times, and so this is my probability that if someone randomly prepares a sandwich, it will be a tuna sandwich on a French roll. Now let's look at and versus or. In my previous problem, I was actually using the and versus or principle, but I didn't point it out to you. I wanted a French roll and I wanted tuna and I wanted 3 toppings. It wouldn't make any sense to say French roll or tuna filling or 3 toppings. I don't want to walk out of there with a pile of tuna in my hand. I want it on a sandwich, and so I need all of those. Here's why that's important. If you have an and problem, you're going to multiply probabilities together. If you have an or problem where either this or that would be okay, then you're going to add probabilities together. Okay, the typical getting dressed in the dark problem where you have a drawer of socks including 4 red, 2 brown, 1 white, and 5 black socks. If you fish around in the drawer without looking, what is the probability that you will find a pair of black socks? Okay, now that sounds like you're just pulling out one thing, but you're not. You're pulling out 2 socks and they're both black. This is really probability of a black sock and another black sock. That's what makes a pair of black socks, right? If it's an and problem, we're actually going to multiply those 2 probabilities together. The probability of pulling out a black sock in the first place would be there are 5 possible socks and how many total in the bottom. So the total number of socks in the drawer would be my bottom number, and that looks like 12. That's the first sock. It's gone. It's out of the drawer and in my hand. So when I go to pull the second sock out of the drawer, now what? Well, there aren't 5 black socks anymore. There's only 4 now. And there aren't 12 socks in the drawer either. Now there's only 11. Okay, my answer is what I get when I multiply these 2 probabilities together because it's an and problem. I can do some reducing first though. Okay, so I end up with 5/33. So I have a 5 in 33 chance of pulling out an actual pair of black socks. Now what would an or problem look like? It's different. Let's see. Find the probability of pulling out either a blue sock or a red sock. Either of those is a winner, and the total number of socks I am pulling out is only 1 sock. I'm not pulling out a pair this time. This is an or problem. So I'm going to find the probability of blue, and then I'm going to find the probability of red, and I'm going to add those 2 probabilities together. That's the difference with or. Remember how I said sometimes probability is 0? This is one of those times because there are 0 blue socks out of the 12 socks in the drawer. What about red socks? We don't subtract any socks because it's an or problem. We're only pulling out 1 sock. What is the probability of pulling out red? It would be 4 out of the 12 socks. Those are common denominators, so this is easy as could be. And that reduces to 1 out of 3. So you have a 1 in 3 chance of pulling out either a blue sock or a red sock. And that's the and versus or principle. I'm hoping that one of the things in the video was new to you, and that's probability.